So we are going to see. Last time we saw how space translation and how this quantum mechanical formalism, how it just transforms or translates in the symmetry as far as space is concerned. So now in the today's class we are going to see how the time invariance, the symmetry of time. So we are oblivious whether time is in forward or it's backward. The operators, the quantum mechanical or the symmetries of nature in time, or rather, it's called time translation. So time translation, we know that in symmetries of nature there is time translation invariance. It's that the laws of nature should not depend upon the clocks, whether forward or backward. So assume that time is linear. So, so the time dependence of state vectors, time dependence of physical state vectors may have, so the results psi of tau goes to t plus tau by an arbitrary amount of. So if there's an arbitrary amount of tau by this the evolution of this psi. So we should have that. So if there is a linear unitary operator, linear unitary operator, we are going to later see. Also can also include a antilinear operator that we have used previously, but that introduces some certainties which we are going to see. But if you assume that there is a linear unitary operator and it's operating on this psi state, so it should not, the time translation invariant should not differentiate between tau plus tau. So evolution of wave function psi when we have an operators. So on this side, so it should be oblivious or it should not matter if it's evolved in time t or time t plus tau. The way previously it was x plus x prime, that was space invariance. The same way we should have this if it is like that. So if it's like that, point is that because tau is a continuous variable, so it's possible to express u tau in the form of, we can express, so if you remember, we just expressed this operator in this thing when we had an operator, we had an approximation of that operator ultimately t in terms of, so we just had an approximation, we could write it as this iota theta t mu theta. So in operator formalism, we just had an approximation for n going to be large, infinity. We could use this in the operator formalism. We can use it in this term. So in the same, we can introduce an Hermitian operator, minus h by h, such that the Hermitian operator, so u of tau, is basically exponential of minus iota h by t into tau. So where h is the Hamilton, So introduce a Hermitian operator h over h, and such that u tau can be written in this term. in terms of Hermitian operator. So this can be taken as a definition of a Hamiltonian total energy of the system, and setting t is equal to 0 means that this function, this thing psi of t, u of tau should be equal to psi of t plus tau. So this thing. So if you set t is equal to 0 and replacing t by tau and taking t is equal to 0, so this psi of t can be written as exponential of minus iota ht by h into psi of 0. It's equivalent to psi of 0. Psi of t is equal to 0, psi of 0. So it will be psi of t is equal to exponential of minus psi u is psi of t is 0. So u is so we have replaced this with this. So psi of t can be written as this, and psi of t is 0. So it's psi of 0. So that's it. So like symmetry, we should have, if we want to have an inner product of the two things, then phi of t should be equivalent to, so inner, if the in a symmetry on the application of linear operators which are operating, the inner product or the scalar inner products should be invariant, such that phi of t into psi of t should be equivalent to phi of 0, psi of 0. It should give the inner product invariant. So if you apply this, if you have a differential equation applying on this, applying a differential equation on this, so it will be what? Psi of dot will be equivalent to, if we have a time derivative which is attached to it, it will be d psi by dt, that will be psi dot. So in this here, it will be iota h cross will come out. So it will be h will come here on the left hand side. So it will be iota h. So when we differentiate it here, iota this will come. So h will go here, and iota square its plus minus will come. So we'll say iota h psi dot. It will have the form h of psi of t, psi of t. So h will come out. So exponential of iota this, it will be in the form of psi. It will be this form. So if this is a time dependent, we see this is time dependent Schrodinger. Our time dependent Schrodinger equation for the state vector psi. For the state vector psi, this is time dependent Schrodinger equation. Now what we are going to do, so this is a general version of time, it's a general version of time dependent Schrodinger equation. So here we have seen evolution of state psi with respect to time. So this in the language, if you see any book on quantum mechanics, so it's also called, commonly called, or generally called Schrodinger picture. So this formalism where we ascribe uh, time dependence to physical states is called Schrodinger picture. So there is another way of equivalent way of saying the same thing, and we'll go to show, and that's called literature, or that's called Heisenberg picture. So in the Schrodinger picture, we say there is a time dependence of physical states. We ascribe time dependence to the physical states. So in the another picture, it's also called Heisenberg picture. Heisenberg picture, and these two formalisms, Schrodinger picture and Heisenberg picture, are somewhat equivalent. It's the same thing, but stating in two different ways. So here there is a time dependence to the physical states, and in the Heisenberg picture, we say we keep state vectors fixed, but by describing state in terms of taking appearance, will suggest we ascribe we ascribe we ascribe time dependence to operators. So here in this one we ascribe time dependence to the physical states. Here we ascribe time dependence to the operators. This is the same one and the same thing. So, but we describe time dependence to operators, which represent as observables, representing observables. So in this we keep state vectors fixed. State vectors fixed. Keep state vectors fixed. By describing state in terms of appearance at fixed time, for example, at t is equal to 0. So we are keeping state vectors fixed. And basically ascribing time dependence to the operators, which are identified or represented with vis-a-vis observables. So now we can define operators in the Heisenberg picture as operators can be defined as so AH can be defined as an operator, can be defined as exponential of minus iota h t by h. A times exponential of minus iota h t by h. So we can have this way we have represented it. Now we can note that h will commute with this, so it will commute with this. So what can we say? So we can say that exponential of iota ht by h, since h commutes with h, so we can say it exponential of minus iota ht by h. This will give h back. So the Hamiltonian is same whether it's in a Heisenberg picture or whether it's in the Schrodinger picture. So if you define this operator like this, so So, so the time dependence of the operator, the time dependence of the operator, the time dependence of the operator in the Heisenberg picture can be given by. So if you have an AH dot, you can see it. You can have a small exercise here. You differentiate dA by dH dot dt. So if you have exponential of iota h t, so if there is not an explicit time dependence, you can have iota by h outside, and in the second term we will have minus iota by h outside, and if you write it in a compressed form in terms of a bracket formalism as a commutator of this and this, so we can write it as ah dot can be written as iota keeping out, so h this ah t by h. You can do it, it's a one step, you can do it here, or you can do it here, like for example, you can do it here. So it will be exponential of, since there is no explicit dependence on, so it will be 1 by h outside, h exponential of minus iota h t by t. In the second term, it will be minus iota h by h exponential of minus iota h t by t into exponential of iota h t by t. So if you keep it's h here, so it will be h iota h. So you can write it as internal commutator, and this thing as e. This was an e, so e is outside. This is out. So you can sorry, e. You can write it as like this. So, so the time dependence of the operator, provided that A is not explicitly dependent on time. On time. Otherwise, if it would have been explicitly dependent on time, would have iota h by h. It would have been so explicitly dependent upon time. So once you differentiate it, so it would have, there would be a problem here. So any Hamiltonian that doesn't explicitly depend on time, so it's a sort of conserved. So in that sense, the ah dot, the commutator will come out to be zero. The commutator will come out to be zero for any conserved quantity. So this means that expectation value of observables are time, whether we use so expectation values are, which means the commutator came out to be 0, so you can associate symmetry to it. So for if an observer sees a state psi evolving according to psi t evolves according to iota ht by h into psi of 0. If an observer sees a state psi which evolves according to this state, then another observer for whom laws of nature are the same must see u psi t. So we are operating. So must see u operate. This another observer must see operating as ht h u of psi 0. So that's for fine. So in order for this to be consistent with the equation, in order for this to be consistent with this equation, in order that 2 should be consistent, we must have exponential of iota ht by h mu is equal to mu times iota ht by h. So you will come to our previous definitions, how we just arrived at how we define unitary operators and the properties of adjointness or inverse. So which we stated that provided that u is a linear operator, which means u inverse h u is equal to h. So that the Hamiltonian must be invariant. Hamiltonian must be invariant under symmetry transformation. So the way the commutator came out to be 0, there is no explicit dependence on time, so which corresponds to symmetry. In the same way, we can say that Hamiltonian must be invariant under symmetry transformation. If u is a linear operator, so if you want to translate the same in the form of bracket, in the bracket way of writing the same thing, which should correspond, the Hamiltonian should be. So we say that Hamiltonian and t should be equivalent to 0. Where, if you remember, we defined operator here as 1 plus iota epsilon t plus ot square. Sometimes this t was associated with p. This is an operator, Hermitian operator. So this Hermitian of this Hamiltonian, this t operator for infinitesimal changes. So these are represented by the generators of symmetries of Hamiltonian which commute with Hamiltonian. So if its invariance under space and time translations, so if there is invariance under space and time translations, which we have conserved quantities associated with energy and momentum. So they are in classical mechanics. So if we have, according to Nernst's theorem, a symmetry to each corresponding symmetry, there is a conservation law. So in the same way, if the bracket commutator of this bracket comes out to be 0, where it is the operator h, the Hamiltonian. So it's that is represented by the geometries of the symmetry of the Hamiltonian, which commute with the Hamiltonian. So its invariance under space and time translation that are responsible for conservation of momentum and energy. So now I'm coming to where we started. So if we replace this linear operator by an anti-linear operator, will the story be same or it will not be it will be different? So that's the point. So if you see, then if it is an anti-linear operator, then this you have to define for if it's an anti-linear operator, anti-linear operator. So this equation comes out to be. So this equation comes out to be. So we'll not have this. We'll have this anti-linear operator. We have to define this as like this. HU is minus H instead of H. So what will it give? The sort of change it will give. It means that the eigenstates phi. I have eigenstate phi with the Hamiltonian H with energy E would have another eigenstate U phi with energy minus E. So which will lead to conflict. So it will lead to some negative energy state, and which will contradict our idea of how we define the stability of the matter. So this is an important point. So how we have to, so if we have formulated this thing, if we assume that anti-linear operators should not leave things unchanged, how we can correct this if this thing, so if it leads to anti-linearity so we'll have some changes or have some change of definitions which can incorporate anti-linearity and which will account for some stability of matter in that sense. So what we will do, so we'll do one thing. So if the symmetries are to be represented via anti-linear operators also as anti-linearity as a condition also, the way we have used previous things also, then we should say that such symmetries, so this is an invocation, reverse the direction of time. So it's an interesting thing. So we can formalize from first principle if we don't assume that the time reversal symmetry is obeyed universally. If there is a partial, we are going to do with this assumption, then anti-linearity as a property can be taken from the ab initio, and which will explain things, which we'll see how. So it has been seen, for example, so we'll see u of psi t, so can be written as exponential of iota ht by h u of psi of 0. So we'll see. So here it's minus, here it's plus. So here it's minus, here. So we have for incorporating anti-linearity, the Hamiltonian is prefixed minus, here it's plus. So if you do that way, so our things will fall in line. So in the place of this equation, so exponential of, so then this thing, minus, here it's minus, it will be plus, iota ht by h into u. It's called u times exponential of minus iota st by. So this is the thing. So where u is anti-linear again. So that the point is that which again is that u commutes with h, avoiding the disaster of negative energies. This is how we can bypass it. The thing is, so question is that this change, if we change t to minus t, it leads to some. So it's that we have formalized thing theoretically in order to just incorporate anti-linearity, the properties of operators. So the thing is we are studying nature, but it is seen that there are some theories, particularly in weak interactions, where time reversal as a symmetry doesn't hold. So we can invoke this thing that in some physical phenomena we can say that a time reversal doesn't hold. So we can the forward and direction we can have the flip sign can be incorporated, and which could explain the things. It is what it's for t going to minus t. The nature respects symmetry under t going to minus t. So we know that symmetry is violating, although it's a good approximation even there. There are, however, transformations that reverses both directions of time and space, and also interchanges matter and antimatter. So we can not only incorporate a time reversal as an idea, we can also have matter as well as we can have proton and antiproton, electron and the way we have matter and antimatter. So we can have all sorts of these operations. Like even in black holes, we have white holes, black holes. So how we can basically see evolution of states and the way these conserved systems are defined, the Hamiltonian and the commutation relation. How we can get conservation principles out of those symmetries and incorporate all these things. And it will be interesting to see how in the physical phenomena we are interested in getting these things. So the other part is that not all operators commute with the Hamiltonian. For example, under Galilean transformations, we can say again. So we can have, if we see that in Galilean transformations, the law is x goes to x plus vt. So the idea of time here doesn't change from one reference frame to another reference frame. So the way we have Galilean symmetries, we also have Lorentz symmetries. How the notion of time is modified depends upon the reference frames. But even though there should be symmetric invariance, and how we have to define this commutation relations and operators, so it's another part of the story. So in the sense, so if we write in the briefly, I'll just write, if we briefly write linear unity operator here as xh t u of v is equal to xht plus vt. So it's it's another interesting story how we can define things. So I'll postpone it, or I will leave it as an exercise for you to fill up the things that how these symmetries, when we have Galilean symmetry, now we don't have Galilean symmetry, we have Lorentzian symmetry, and in Lorentzian symmetry we should have not only translations but rotations but boosts also. And accordingly we can define these conserved quantities, and how can arrive at a commutator, and how define an operator like this, and incorporate there, and see how the conserved quantities come out there also, in presence of Lorentz symmetries, and the notion of time transmission. That's also an interesting thing which done in the follow-up book. So I'll stop here.